Good afternoon and good morning, everyone. Welcome to Swiss Korean Science Club Robotics Inspired by Nature. I'm Tian Lee, Junior Project Manager at Science and Technology Office of Embassy of Switzerland in Seoul. We're part of the Swissness Network, the outpost aimed at connecting Switzerland with the other world's innovation hubs. Science Club highlights and promotes ongoing and potential Swiss-Korean cooperation in diverse fields of studies. We organize the Science Club generally in the embassy. However, with the COVID outbreak and the current social distancing measures, we switched it to a digital version, which actually offers the delightful opportunity to be connected with our partners in Switzerland and any other part of the world as well. So it is our great pleasure to welcome you all here. Today's Science Club will start soon with two speakers from ETH Zurich and KAIST, Korea Advanced Institute of Science and Technology, under the moderation by Mr. Nicola Nosengo, science writer at Swiss National Center of Competence in Research, or NCCR. I genuinely hope this Swiss Korean Science Club will offer every one of you a great time to learn about the latest research that's going on in Switzerland and in Korea, and also that it'll open up new opportunities for potential cooperation and joint projects in the nearest future. Thank you very much, and Nicola, now the floor is yours.
Thank you very much. Thank you very much for the introduction, and thank you very much to the organizers for having us here today speaking on these very interesting topics. I'm Nicola Nosengo. I'm the science writer and communication officer at NCCR Robotics, which is a Swiss consortium of 7 research institutions and more than 25 laboratories involved in robotics and artificial intelligence. And the topic of today's talk is robotics inspired by nature, or bio-inspired robotics, as it is at times called. Now, this line of research stems for a very simple observation: the fact that most living organisms, even the simplest ones, from insects to mollusks up to mammals and of course humans, display abilities that robots would strive to have, would badly need to have, but that are very difficult for robots. Most animals can move faster and more efficiently than robots. They can easily switch between running, walking, jumping, swimming, while most robots are confined to just one way of moving. Most animals can grasp, manipulate objects. Think of the manipulation abilities of humans, of course, but actually most animals have them. Possibly most important, animals can easily adapt to environments they have never encountered before, whereas most robots, think of the typical robots that work in today's industries, need to work in predictable environments that have been designed specifically for them. So whereas most robots need an environment that is adapted to them, living organisms can adapt quickly to their own environment. And as you can imagine, this is an ability that would be fundamental for having robots operate in unpredictable and chaotic situations like a disaster scene, like a search and rescue scenario, but also for the inspection and maintenance of an industrial site, but actually also for many applications that could take place in homes and that involve having robots being around humans, work closely and safely with humans. So our two speakers today, as many other contemporary roboticists, are trying first to understand how living organisms pull off these tricks, because it is often not entirely understood, and then to turn this knowledge into engineering principles that can be applied to robots and designed a whole new generation of robots, more autonomous, more capable of adapting to unpredictable situations, and so in the end, ultimately being more useful to humans. So our two speakers today, who I ask to turn on their camera and being seen by the audience are Marco Hutter, who is an assistant professor at ETH Zurich, and Professor Haewon Park, who is a professor at the Korean Advanced Institute of Science and Technology. Now, a few more words about Marco to begin with, because he will be our first speaker today. Marco Hutter is a mechanical engineer by training. He did a PhD at ETH Zurich, where he's still active and is still working. He's mostly interested in the development of hardware, of machines, and also of new actuation concepts and new control methods, in particular for locomotion and manipulation. And among many things, he has developed a quadruped robot called Animal, which is now one of the most popular platforms of this kind. And I think we will see a bit about Animal in his presentation. And he also co-founded a spin-off called Robotics to further develop this platform. Marco Hutter is also a member of NCCR Robotics, as I am, but he is also a member of a similar Swiss consortium dedicated to digital fabrication. So he's also very active in that field. He has received several awards from the Branko Weiss Fellowship to the Early Career Award of the IEEE Association to a starting grant from the European Research Council. I'm looking forward to hear Marco present us a few examples of how he develops robots that are inspired by nature. And just a brief reminder to the audience that we will have the two presentations and a Q&A section at the end. But throughout the presentations, you can use the chat tool to write your questions or any specific request for technical assistance that you may have to better follow the presentation. And at the end of the two presentations, I will pick up your questions from the chat, and we will have some time to discuss with the speakers. So with that, I leave the floor to Marco Hutter for his own presentation.
Thanks a lot, Nicola, for the introduction. I'll take over here, sharing my screen. Great. So I hope you can all see it. So thank you, Nicola, for the introduction, and also Gian for hosting the Science Club here on robotics inspired by nature. As Nicola, as you mentioned before, my research is about legged robots. So the one that you see here in the middle of the three dogs. And this field of legged robotics, this draws really a lot of inspiration from nature. In this brief introduction presentation, I would like to tackle two elements and show a little bit in how we take inspiration there from nature. First one is talking about actuation, and the second one about control. And I show you how we can take inspiration here from nature to make our robots a little more capable. Now, when I started research in this field almost a decade ago with my PhD building some of the first quadrupeds that we had at ETH, what I did first is that I bought a small dog. And what really fascinates me about dogs is that they really combine all kinds of different excellent skills in one unit. So first, dogs are extremely fast. Not quite as fast as a cheetah, but of course they're still very, very fast. Second, they're extremely versatile. So almost any terrain, they can get across it, they can easily adapt to that. Third, they're very efficient. So give them this amount of food and they will just operate for the whole day. And fourth, they're also extremely robust. So don't worry, the dog was never harmed. It's actually just sitting below me, so everything is still in good shape. Now, the reason to achieve that to a large extent is due to the fact how these animals are built. So we took one of the dogs to our office space and put it on a treadmill. And if you look a little more carefully, you see that dogs are actually pretty compliant. They have a rigid links for the bones, but then the actuation, like composed of muscles and tendons, acts very compliantly. And that helps dogs and also any other animal and humans, in particular while running, while doing dynamic maneuvers. In fact, there has been extensive studies about that, in particular by the biomechanics community, to analyze how does that muscle tendon system help animals to locomote. And what they figured out is that this mechanical compliance that is integrated by these muscles and tendons increases robustness of the system. So if you get external disturbances, what this does, it just leads to a deflection of a compliant element, but it doesn't really harm our muscles. It allows us to do energy storage temporarily, and then also to release this energy in very short time, and by that increase the peak power of our actuation. And last, and I think this is really the most important aspect for us from also controls perspective, it turns a position controlled system into a force controlled system. And taking inspiration from that, we went into the robotic application and changed the way how classical robots were built. So a classical robot is typically composed of a motor and a high gearbox reduction that directly drives the link. And with this system, what we want to achieve is that these industrial robot arms follow predefined trajectories very precisely, independent whether they're carrying here a 200-gram screwdriver or a 200-kilogram motor block. So any disturbance is just canceled out. And this would be extremely harmful if you would place them in an unstructured, unknown environment. In contrast to that, by including now compliant elements, just as the muscle tendon system has between the gearbox output and the motor, and decoupling these two dynamic elements, you essentially get a much more dynamic and force controllable system. So using these principles, we generated a series of quadrupeds over the last decade, which ended up in this animal series. First ones were really done in research environments in the lab for like just studying the fundamental principles of locomotion, dynamic locomotion. Then we had a couple of research prototypes that we could take outside into the field, and which we also shared with a couple of researchers around the world. And in the meanwhile, there's a company really industrializing this as a product in order to have it useful for industrial inspection. Now, what I would like to do here is to have a little bit of an in-depth analysis of what happens in dynamic maneuvers like this and how these compliant elements can support something like that. What I show you here is the stance phase, so the time between landing and liftoff of this quadruped doing a dynamic maneuver. And you see in green what the knee is typically doing. So we have this classical motion. When we land, we first go down into the knee, crouch, decelerate, and then reaccelerate until we jump off again. Now, what is very interesting to see is that the motor now, thanks to this compliant element, doesn't have to do this full motion, but instead it can directly go from a landing to a liftoff configuration. And this has a pretty big impact on the power and velocity side. So what we're looking at here is the power during stance phase. And you see again, like in the first phase, this green line is negative. So we are actually decelerating the system. And then only the second phase, we are reaccelerating the system. This is like stop and go traffic that you have in the car, but then your motor continuously pumps energy into the system. And by that, you're becoming a lot more efficient. If you put this in numbers, there's about 60% of energy that is stored and released purely mechanically, purely passively. The second element is that the peak power that the motor produces here, this is about only 1/4 of the peak power that we see at the joint. So in other words, we can have a much smaller motor, still achieve high peak power, and by that make a system that is more dynamic. Now, what interested me at the time is that if you compare this now to biomechanical studies, so this was a study done by Roberts in 2002, biomechanists who analyzed what happens in the Achilles tendon during running. And you can see that the curves here, they look very similar. So in other words, what we see in muscle tendon system during running on the biomechanical side is really something that you could replicate here to a certain extent using so-called series elastic actuation. The second aspect, which also Nicola introduced at the very beginning, that I want to talk about here is about control. and dive there a little bit into what the general public often calls artificial intelligence. Or better in our words, how we can use machine learning and neural networks in order to control robots. So this is in contrast to the classical model-based approaches. Now, to do machine learning, to learn for a robot, we need data, and we need a lot of data. So typically what we're trying to do, or what we're doing, is like we're using simulation in order to generate massive amount of data at almost no cost. We can do this much faster without destroying robots if things go wrong. The second aspect which we integrated in our research, and which turned out to be pretty crucial, is that we also went to the real systems and took information from the real system in order to bridge the gap between what you're simulating and what you see on the actual system to make the simulation much more accurate. And a second reason why I would like to show this here is because this is work by two brilliant PhD students that were in my group, Jimin and Juno. Jimin, in the meanwhile, is already at KAIST, and this shows a little bit in how this collaboration between Switzerland and Korea is already working today. Now, if you do this, you can start to learn to locomote. So the more you learn, the better you get, until you have a machine that can really walk around. As you've seen in the intro by Nicola, like one of the key aspects is that we have machines that can adapt to different types of environments. And this is also something that we looked at here, and that's actually the only slide where I dive a little more into technical details. So how can we make these robots now adapt to arbitrary environments, not only flat ground that we have in the lab, but like loose gravel, slippery, icy surfaces, snow, and even in like vegetation where it can get stuck. Now, the trick that we applied here is that we took in simulation, we trained a teacher policy, which takes a lot of privileged information. So things that we can generate in simulation, but we typically don't know about the environment, like the exact contact states, contact friction properties, the exact height profile, and stuff like that. And then we trained a student policy, which we deployed actually on the system, that tries to figure this information just purely out from proprioceptive information, so from experience, while walking through a certain surface, to recover the same information that you generate from privileged information on the robot. And we paired this with an adaptive terrain curriculum learning, so the better your robot becomes, the harder you make the environment, such that you challenge the robot more and more until you have policies that allow the machine to walk over almost arbitrary types of terrain. And we took this and we put it on a real system, and it really turns out that it just generalizes beautifully. So we could all of a sudden walk across terrain purely blindly without having everything about the environment modeled in detail. You could take the robot out of the lab, bring it to some nice scenery in the mountains on hikes, where the robot really has to deal with like very challenging grounds, loose grounds, slippery surfaces as in this riverbed, or even vegetation where the robot might get stuck. And that shows a little bit on where this mobility can go in the future and what kind of applications that one can envision in the near term or even midterm. A few interesting aspects which are also seen in nature to a certain extent. So what you see here is the robot walking onto a step that the robot doesn't see. So what happens is that the robot starts walking, and then it hits that obstacle. Now it remembers that there's an obstacle and triggers the reflexes and gets around it. So these are elements that previously had to be handcrafted. And now with this new technology, we could actually generate neural networks that remember about this and use that in order to trigger reflexes. Similar behaviors when going on very slippery grounds. So you see how the robot walks on the slippery surfaces and immediately adapts the behavior. And that's also something that before it had to be like tediously handcrafted, and now all of a sudden we have methods that really allow us that the robot can estimate friction coefficients. So as soon as we start sliding, we walk a little more carefully, and then once we have again like great surface under our feet, we walk like in a normal way. You can also start combining different behaviors and do all kinds of crazy maneuvers. So here is how to combine self-rightening, standing up, and locomoting in a clever way. And these are behaviors you can generate with that. So you see a robot that falls over, realizes that it falls over, recovers from that, and keeps operating. And actually can put it in an arbitrary configuration on the ground, and the robot will figure out the way to stand up and continue to operate. I think it's a very nice demonstration of where mobility can go in the future, what we will be able to achieve with these types of robotic systems, and hence also what type of applications that we could possibly tackle in the future. And with this last element here, where I show you where this robot is deployed, I want to then also come to the end of my introduction talk here. So you see here 4 different areas where we deployed it. What top left is a inspection or exploration mission that we do during the DARPA Subterranean Challenge in a nuclear power plant in the US. So this robot is left free at the entrance, and it has to go into this nuclear power plant, explore the complete environment, figure out how it looks like, assess situations if there is like a danger somewhere or not, and you see how the robot maps the environment, detects free spaces, and moves around autonomously. On the bottom left, you see an inspection routine on an offshore site in the North Sea. Then we have inspection and surveillance for safety purposes on construction side and bottom right. And here on the top right, you have sewer inspection in Zurich. For example, City of Zurich has more than 100 kilometers of walkable sewers where we're sending on a daily basis 10 people walking in the street of Zurich to figure out whether everything is operating the right way, if there's cracks, if things are stuck. And these are jobs that in the near future, I would like that the robots will take over. So let me conclude here with a few statements about why I think that natural or inspiration from nature can help us a lot in robotics. The first thing is that nature is really a great source for inspiration. But vice versa, also robotics can help us to better understand nature. By showing principles in robotics, we can help biomechanists and biologists in like understanding, interpreting some of the findings in nature. Second, I think it's important to understand that biological systems and robotic systems, they are distinctly different. So we should, in my eyes, really not try to copy nature, but rather take ideas, borrow ideas from nature, and then use that, but exploit the strength that we have in robotics. Third, I think nature is also helpful as it's a great source for feasibility or as a feasibility demonstration. So it demonstrates you already what is possible given the constraints of physics that we have on Earth. And knowing that something works is also already a pretty big hint whether you should do it or not. And it's also a hint in what kind of requirements that you need in terms of energy, power, what size of a robot you might design for a certain task. And it also tells you a little bit of what is a possible solution for the problem you want to achieve. And then lastly, and I think this is very important for us researchers, for me, it's like a really great motivation for research. And I think that there's still so much we can do if you look at the performance of nature, that there is probably another 50 years of research ahead of us. With this, I'm concluding here. Thank you all. If you're interested in more information about our group, about our robots, check out the homepage and YouTube channels. I stop sharing here and give back to Nicola.
Thank you very much, Marco. Thank you for this fascinating presentation. I have to say that the videos of animal walking in the forest are particularly fascinating and really give an immediate sense of how powerful bioinspiration can be for robotics and how robots are, let's say, beginning to close the gap with the versatility and power of living organisms. I remind the audience that you can ask questions, comments, or whatever also during the talks by using the chat. We will discuss them at the end. And I now hand over to Professor Haiwon Park for his own presentation. Now, a few words about him. After graduating from Yonsei University in Seoul, Haiwon Park worked for
Nicola, you muted yourself.
Sorry, this had to happen at some point. So I was introducing Professor Haiwon Park, just saying that after graduation in Seoul, he spent a research period in the USA, first as a PhD student at the University of Michigan and then at the University of Illinois. Now he's working as an assistant professor at the mechanical engineering at the KAIST, the Korea Advanced Institute of Science Technology, where he also heads the Humanoid Robot Research Center, in addition to being heavily involved, of course, in research on bioinspired robotics. In particular, is particularly interested in control dynamics and mechanical design of bioinspired robotic systems, not only walking robots and not only quadruped robots, as we will see in a minute, but he will actually show us a rather different angle on bioinspiration in robotics. So with that, I leave the floor to Haiwon Park, and we'll have some time to chat about both presentations at the end.
Okay, now I'm sharing my slide. Okay, so yeah, thank you, Nicola, for a nice introduction. My today's topic is about bioinspired designable legged robots for multimodal locomotion. Before I talk about this topic, let me introduce myself and my lab. So I'm currently director of Dynamic Robot Control and Design Lab at KAIST. The lab initially started at the University of Illinois when I was a faculty member there, and moved to the KAIST in 2019 when I moved to KAIST. And the lab is now part of the Humanoid Robot Research Center. And also I'm director of the HUBO Lab, Humanoid Robot Research Center. And in total, we have 8 PhD and 9 master's students. And on the right bottom pictures, you can see Jamin, who worked with Marco for his PhD, and Juno Oh, he's founder of the HUBO Lab, and Haiwon, me. We are actually a part of this HUBO Lab, a wonderful HUBO Lab. And our research interest covers humanoid robot, quadruped robot, and bioinspired robot. Since today's topic is about bioinspired robot, I will mainly focus on these two robots here. Okay, so flying squirrel and quadruped robot Bambi. So let me show my research research video. This is my master degree topic, which is a dolphin fish robot. And it can actually swim up to 1 meter per sec. And it can make a turn left or right. And the second video is about my PhD topic, which is Mabel, bipedal robot Mabel from University of Michigan. And in this video, the robot able to walk over uneven terrain with blindfolded. So you can imagine that this robot has to walk on uneven terrain without any vision sensor. And after that, I went to MIT. This is probably very famous video on YouTube. This is MIT Cheetah 2 robot running and jumping over obstacles. So here I use the vision sensor to detect the obstacle and plan the jumping motions on real time. And after that, I joined University of Illinois, and I made some quadruped robot, which is able to balance, and it's a really small size robot, but has the ability to calculate all the forces and then all the state estimation inside of robot. So the robot able to overcome uneven terrain and rough terrain utilizing the model predictive control approach. Okay. So I now more focus on more like control side of the robot, but the topic of this webinar is bio-inspired design lab robot. So I will talk about bio-inspired design lab robot. So probably one of the most famous bio-inspired robot is Stanford Gecko robot from Stanford University, made by Professor Sang-Bae Kim and MIT. So this robot uses nanostructure to enable vertical wall climbing. And also the MIT Cheetah robot utilizes bio-inspired design. So they utilize tendon and bone structure observed in the quadruped animal and implemented this idea into the leg design to reduce the stress in the bone. So when we design this kind of robot using bio-inspiration, we usually follow this kind of process. So first of all, we define the functional goal we want to achieve in the robot. And we looked at the biology, how this biological animal achieves this functional goal. And we try to implement and devise, some robotics mechanism utilizing many the tools in robotics. So for example, analysis and simulation, engineering design and implementation, and finally experimental testing to verify the functional goal has been achieved or not in the robot. So in this talk, I will provide two examples of this process. First one is, first functional goal that I want to achieve is aerial and terrestrial multimodal locomotion. And second functional goal is a foot design with improved traction. So we will look at the biology. So especially we look at flying squirrel, how the flying squirrel achieve aerial and terrestrial multimodal locomotion. And we look at the foot design of the cat. And I will talk about engineering design and simulation and experimental testing of this mechanism. So, okay. But before we go on, we have to take consideration of these topics. So because the animal and the robot, they are different system and mechanism. So we have to take into account this consideration into design of the robot. So first of all, the animals has a lot of degree freedom, usually go more than 300 degree freedom. We cannot have 300 degree freedom in our robot because it can be too complex and too heavy. So usually the robot's degree freedom is much less than 50, and their actuation system is different. So in robot, usually the motors are used for actuation, while in biological system, muscles are used. And the material and component is different. Where the robot is usually made with a rigid part, while the biological animal has a soft and rigid part as well. So sensing capability is really limited in the robot, while in the biological animal, it has like whole body sensing in for detecting the contact and the stress on the muscles, something like that. So we have to take this consideration into the robot when we design the engineering system. So the first example is a multimodal glider and walker. So we want to divide some robot system, something in between aerial locomotion and versatile terrestrial mobility. So like animal robot and person like spot. So we look for solutions from the biology. So biological animals like flying squirrel can vertically climb up the tree and glide from the tree in order to reach another tree, and it actually modulate its control input, such as like shape of the wing, in order to modulate aerodynamic forces. Okay, so if you use a gliding trajectory of the flying squirrel, it actually composed of 3 phases. So in acceleration phases, it gains the speed sufficient to manipulate the aerodynamic forces. And after it gained the speed, it utilizes the wing shape to have a stable gliding. And near the end of the gliding trajectory, it prepares for landing in order to reduce the impact from the landing. So from this gliding trajectory, it can reach up to 2.4 gliding ratio, which is a ratio between vertical distance and horizontal distance traveled. So for this gliding performance capability, the flying squirrel has 3 main features. So first of all, so in addition to the wing surface between front and rear leg, it has additional aerodynamic surfaces such as here and there and tail, and it has some bundle of thicker bundle at the boundary of the membrane in order to make the edges rigid, and it has a wingtip here in order to reduce drag induced by vortex. Okay, so this wingtip is really similar to the winglet of a commercial airplane. Okay, so we fabricated a silicon membrane wing in order to mimic the wing design of the flying squirrel. So first of all, we have a silicon membrane here, and we have an additional wing surface like here. And we have a thick bundle, which is made of the rubber string, okay? And we have a winglet, wingtip, made with the ABS, plastic. So after this membrane design, we did a simulation in order to check that the robot can have enough gliding ratio, and while gliding in stable manner, and being able to change the gliding speed or gliding pitch angle. So there are 2 main control surfaces in the flying squirrel, which is wing and tail. So we have a simplified model of the wing and tail here, and our control input to control the gliding behavior is wing angle and tail angle. Okay, and so we have aerodynamic forces model, which is lift force and drag force, and we have an equation of motion to explain how this, the gliding behavior will be emerged from the control input. So when we did the simulation, we found that the gliding ratio of the robot will be 2.14, which is about the same amount of gliding ratio of a flying squirrel, and velocity and angular vertex and body pitch could be stabilized with our design. And we further checked that by changing the tail and wing angles, we can change the gliding velocity and body orientation as we wanted. So after we fabricated the membrane wing, we checked we have experimental on the wing. So on the left, we have a wing design with elastic cord, and on the right, we have a wing design without elastic cord. You can see that without the elastic cord, the wing fluctuates much more than the design with the elastic cord. So we can see that the effect of elastic cord design. Also, we did some safety simulation to check the validity of a wingtip design. You can actually see that volticity has decreased a lot, and this decreased volticity will decrease also the drag force. So we checked that wingtip design will be effective in reducing the drag force. So this the wingtip design, we designed with mechanical, passive mechanical design. So this wingtip should be retracted when it's walking. So we don't want to add one more actuator in order to enable the switching between the retracted wingtip design and straight wingtip design. We devised some passive mechanism. So simplified passive mechanism. So with all of these design features, we could make a flying squirrel robot, which is about 400-200 gram light, heavy, And we fabricated silicon wing with a thickness of 150 micrometers. And it has 13 RC servo motors to control the wing surface as well as working motion. So this is an experimental video. So you can see that it actually changed the angle of attack in order to reduce the velocity, landing velocity. And this is a frontal view of the robot. And this is actually longer gliding. My computer got slow, so let me check me again. Okay. So this is a longer gliding from like 3rd floor of the building. So this robot could achieve a gliding ratio of 2.21, while its mean value is 1.88, which is very similar to actual flying squirrel's gliding ratio, as well as we could manipulate the angle of attack and the horizontal velocity and vertical velocity by changing the wing shape. So here is the gliding phase, here is the landing phase. In landing phase, we could observe increased angle of attack. Because of this, we could decrease the x and z velocity, as you can see here. And this robot is able to walk as well using the trotting gait, which is the most common gait used by quadrupedal animal. And because of its versatility, it can do crawling locomotion as well. Okay, so my second example is anti-skid foot design for improved traction. So most of the foot design in quadrupedal robot is just a simple spherical and cylindrical shape, because we usually assume the spherical was rolling contact with the ground. But in animal, it actually, the foot has a really complex mechanism inside using tendon. So it can actually protract and retract the claw. So when the cat needed the claw, it actually protracts, and it utilizes the claw in order to climb up the vertical walls. So when we have irregular surfaces, then this foot can use the claw to enable the vertical wall climbing. So as I explained, the foot has a really complex design, so we cannot just copy that. So we devised this design with the primary feather, which is a rubber, and secondary feather, which is microspine array. So this microspine array will have a larger traction than the primary feather rubber. So in this video, we show the design. So here we have first primary foot design with the rubber pad, and we have a microspine array, complementary pad. And we tested the microspine array foot to check that it has a larger friction, larger traction. So you can see that it has 3 times frictions than normal foot, rubber foot. And now we devised the passive mechanism to switching between those 2 pads. So this design has a wheel and the cam design. So in normal operation, it has a rolling contact, but when it starts to slip, it can trigger activation of the microspine array, which is installed in this pad. Okay. So you can see that whenever it slips, it will activate the microspine array. So by utilizing this, we could make the robot jump and attach to the very stiff slope. So here, because of the rubber pads, we have enough traction without utilizing the spine array. But when the robot lands on the steep terrain, it needs more traction. So this need-based switching mechanism we will deploy the microspline array in order to increase the traction. And we tested this mechanism to various types of the surface, as you can see here. Sometimes this spine array fails to attach to stiffer surface because it could not utilize the irregularity on the surface. So in conclusion, I showed two examples of bio-inspired robot design. And the functional goals we want to achieve in the robot is aerial terrestrial multimodal locomotion and food design with improved traction. And we saw biological inspiration from the flying squirrel and the cat, and we implemented this idea into robotics by utilizing simulation analysis and experimental design and engineering design. So with that, I want to conclude my talk. So thanks for listening. And yeah.
Thank you very much, Professor Park. It was another fascinating talk that I think demonstrated very well what also Marco Hutter was mentioning, the fact that bioinspiration does not mean merely copying nature, but actually studying nature to extract engineering principle and then develop those principles, which is complex engineering work, much beyond copying a nature solution. So thanks to both our panelists for this fascinating, though necessarily quick tour through robotics inspired by nature. It is time now for some questions. I have a few of questions myself, but I definitely would prefer to give preference to the ones from the audience. And in fact, in the chat, we have one, a bit of a technical one, mainly for Marco Hutter from Zazo Mehis, who is asking, do the springs in the legs deteriorate over time or use because of metal fatigue, or do you have a way to prevent this? I think he's referring to animals, I guess.
Yeah. So when we did the first prototypes, very simple, that was an issue. But then once you realize that this is something you want to have in a machine that operates over a long time, you start designing the materials and the actuators for really long-term life cycles. So let's start with the choice of materials. We have now in the latest generation, we have special titanium mixtures that we're using there. Second, what is important is that you design the properties itself such that it can last forever. And the third element is that you do a lot of life cycle tests also on test benches. We have these actuators stressed over millions of load cycles before we actually deploy them on a real system or in a product.
Okay, thanks a lot. I hope that answered the questions. And please do not hesitate to post more questions. But in the meantime, oops, came another one. Yeah, follow up on that question. Maybe we'll quickly move to a different subject. What does now depend the maximum time of life? I guess that
this is very hard to answer in general. There is, like most of the time with systems, it depends on the use case. So if I deploy a robot wrongly in a scenario where it might fall or down a stair or whatever, then I have something different breaking than if I have it walking forever on a treadmill. So this is something that you can't really predict. So we try to have all the components on the nominal operation to last for the time that these robots machines are planned to operate in a nominal condition. But then if you have extraordinary events, you can lose feet, you can break something, you can also break springs, you can destroy, possibly even destroy a gearbox if like everything goes wrong. For us right now, there is certain elements that wear out over time, and that's feet predominantly. It's like for us, if we have to change shoes after some times, because that's the material that interacts with the environment, and that's where you have a lot of wear.
Okay, thanks a lot. A question from myself. the kind of research you're describing today is by definition very much interdisciplinary. You need a lot of different expertise because you have to understand biology for sure. You often have to use new materials. If you use machine learning, as you've mentioned in your talks, that's a very specific expertise, of course. So there is much more than, let's say, classic engineering, classic and mechanical engineering. So how do you incorporate these different expertise in your projects? Do you collaborate with the labs from other fields, or do you actually hire people with so different expertise in your own teams, or how do you do it? Maybe let's start with Professor Park to see how we answer that challenge.
Okay, so the topic that I presented today, we didn't actually collaborate with any other groups. So, but we look at a lot of ideas from experimental biology, many papers from the biologists, and we actually did some analysis based on the some observation from biology. So we didn't do any explicit collaboration for this topic, but we actually took many observations from the biologist. What I can say is I show some quadrupedal video before the topics, right? So for that project, I'm collaborating with the vision researcher and machine learning researcher and state estimation guy and the animation, the computer animation guy, in order to integrate all the technical aspects into the quadrupedal robot. So this is an ongoing project, so I don't have any good experimental result, but I hope to show that in near time. So yeah, for that, I think Marco had more to say, I think, yeah.
Yeah, let's see from him.
I try to be quick in here. So I mean, robotics in general is extremely interdisciplinary by default, right? We have mechanical engineering, electrical engineering, informatics, and what you're talking here about is just like adding new things on top. So we're running active collaborations because you cannot really have all this information through hires in a group. Otherwise, you would have a group that is just exploding. And actually also goes beyond. I think robotics is an enabling technology for many, many different fields. So you naturally run collaboration with architects, with civil engineers, environmental scientists. So it makes us kind of really a community which is spreading out to many, many other communities. And like this, there's also lots of interdisciplinary workshops, conferences, and so on and so forth.
So there is one more question for the audience. I think we should have time for that at least. It is mainly for Marco Hutter, but it's about quadruped robots. So maybe both can have an insight. I noticed Zubek writes, I noticed that Animal has developed wheeled-legged robots. Compared to, let's say, classical legged robots, which one will have a better prospect? Can wheeled-legged robots replace legged robots? So what's the comparative advantage of that kind of locomotion?
So that everybody knows, so what this is a quadruped, exactly like Animal, but we have wheels on the end effector instead of point feet or feet like Yvonne showed before. And the reason we want to do this is because, I mean, wheels are amazing. And wheels is something that nature cannot develop just because of the fact how natural actuation works, because blood will never circulate through like a fully rotating part. And that means if we want to make systems that might be superior, I think it's great that we're combining what are the big benefits that we have in robotics, in machine designs, with the inspiration that we can get from nature. And we're not just trying to replicate things, but see if we want to have something efficient and fast, wheels are the right way to go. So again, depending on the application, if you're rather on flat grounds and environments, urban environments that are designed for humans and cars and things like that, you might get further with like wheeled-legged systems. While if you go through a forest with dense vegetation, I think this is wrong.
We have one question from Sungmo Lee to Professor Park, actually. For the gliding robot, can you improve the gliding ability just by making the wing larger, or is there any sort of limit to that aspect?
Okay, that's a very good question. Definitely we can improve the aerodynamic, capability by making the wing larger. But with the larger wing, the leg will have longer length and we'll have more torque on the actuator in order to make it work. So we have to strike some balance between the working capability and the gliding capability. So we did some optimization study, both on gliding and walking, like the calculating optimal required torque in order to generate both motions. So yeah, so there's some aspect about that. Yeah.
Okay. So thanks a lot. I think we have some time constraints, so I think we have to close the event at 10 Swiss time, 6 Korean time as scheduled. So thanks a lot again to our panelists today, to Marco Hutter from ETH in Zurich and to Hye-Won Park from KAIST. And just a brief reminder to please do not hesitate if you have more comments, more questions about this event or future or past ones to the Science and Technology Office of the Embassy. You can use actually the QR codes in this screenshot to reach out to the website or to the LinkedIn page, or of course, look for them on the web. And I thank all the participants, everyone in the audience, for being with us today for this very fascinating talk. And I thank again the organizer, the Embassy and the ST office for this brilliant initiative. I know they will have more events coming in the future on other topics, so I recommend to keep following them. And thanks a lot for having me as well.
Thank you very much, Nicola, for your time. And also thank you, Professor Marco Hutter and also Professor Hye-Won Park for your brilliant presentations as well. Thank you, everyone, and stay tuned. Bye-bye.
Thank you, everyone. Bye-bye.
Bye.
Bye.